second order reaction. The rates of bimolecular reactions which occur when two molecules come together, molecule A and molecule B, to give a product, they are frequently described by second order reaction. When the speed of the reaction depends on the concentrations of A and B, with each term raised to the first power, the rate of decomposition of A is equal to the rate of decomposition of B, and both are proportional to the product of the concentrations of the reactants. If A and B are the initial concentrations of A capital and B capital respectively, and X is the concentration of each species reacting in time t, the rate law can be written as dx by dt equals the reaction rate constant multiplied by A minus X multiplied by B minus X, where dx by dt is the rate of a reaction and A minus X and B minus X are the concentrations of A capital and B capital respectively, remaining at time t. When in the simplest case both A and B are present in the same concentration, so that A equals B, then dx by dt equals the reaction rate constant multiplied by A minus X squared. And in this case, dx divided by A minus X squared equals reaction rate constant multiplied by dt. The integration of the previous equation using the condition x equals 0 at time equals 0 and x equals x at time equals t gives the second order reaction rate equation. The equation for a second order reaction is shown in this equation. X divided by A multiplied by A minus X equals K multiplied by T, and the reaction rate constant equals 1 divided by AT and multiplied by X divided by A minus X. The units of the reaction rate constant for a second order reaction is liters per mole per second. When X divided by A multiplied by A minus X is plotted against the time, a straight line results if the reaction is second order. The slope of the line is the reaction rate constant, and half-life of a second order reaction when the concentration of the product equals half of the initial concentration is measured or calculated, and it equals 1 divided by AK. When you have one component reacting with itself, for example, a molecule A is reacting with another molecule A to give a product, then the change in the concentration by changing time equals the reaction rate constant multiplied by the concentration square. In this case, the change in the concentration by changing the concentration square equals minus reaction rate constant multiplied by dt. If the equation is integrated, the following equation for a second order reaction is obtained. 1 over C equals 1 over C naught plus KT. Then if a plot of the 1 over concentration is plotted against if the 1 over concentration is plotted against time, a straight line equation is obtained where the intercept equals 1 over the initial concentration and the slope is the reaction rate constant. These figures show that in case of second order reaction and also in case of first order reaction, a plot of concentration versus time is usually nonlinear, while for a second order reaction, if we plot 1 divided by the concentration, remaining concentration versus time, a straight line relationship is obtained when we have a second order reaction. The slope equals K and the intercept equals the inverse of the initial concentration. Classic collision theory of reaction rates. The Arrhenius equation is largely an empirical relation giving the effect of temperature on an observed rate constant. Relations of this type are observed for unimolecular and bimolecular reactions and often are also observed for complex reactions involving a number of bimolecular and unimolecular steps. Although it is extremely difficult in most cases to attach significance to the temperature dependence of complex reactions, the temperature dependence of uni and bimolecular reactions appear to reflect a fundamental physical requirement that must be met for a reaction to occur. The manner by which temperature affects molecular motion can be understood by considering a hypothetical situation in which all the molecules of a substance are moving in the same direction at the same velocity. If a molecule deviates from its course, it will collide with another molecule, causing both molecules to move off in different directions with different velocities. A chain of collisions between molecules can then occur, which finally results in random motion of all the molecules. In this case, only a certain fraction of the molecules have a velocity equivalent to the initial velocity of the ordered system. The net result is that for a fixed number of molecules at a given temperature and therefore at a definite total energy, a distribution of molecular velocities varying from 0 upward is attained. Because kinetic energy is proportional to the square root of velocity, the distribution of molecular velocities correspond to the distribution of molecular energies, and the fraction of the molecules having a given kinetic energy can be expressed by the Boltzmann distribution law. From the Boltzmann distribution law, this is the Boltzmann distribution law, we note that of the total number of moles, NT, total number of moles, of a reactant, Ni moles have a kinetic energy given by EI. The collision theory of reaction rates postulates that a collision must occur between molecules for a reaction to occur, and further that a reaction between molecules does not take place unless the molecules are of a certain energy. By this postulate, the rate of a reaction can be considered proportional to the number of moles reactant having sufficient energy to react. That is, the rate of a reaction equals Pz n of I. The proportionality constant in this relation is divided into two terms. The collision number Z, which is for a reaction between two molecules, is the number of collisions per second per cubic centimeter, and the steric or the probability factor P, which is included to take into account that the fact that not every collision between molecules leads to reaction. That is, P gives the probability that a collision between molecules will lead to product. Substituting for n of I in the equation, this is the n of I, gives the rate equals P multiplied by Z multiplied by the exponential of minus energy divided by RT and multiplied by NT, which when compared with the general rate law, rate equals the reaction rate constant multiplied by the concentration of reactants. This leads to the conclusion that reaction rate constant equals P multiplied by Z multiplied by the exponential of minus E divided by RT. Thus, collision state theory interprets the Arrhenius factor in terms of the frequency of collision between molecules. A, the constant A, equals P multiplied by Z, and the Arrhenius activation energy as the minimum kinetic energy a molecule must possess in order to undergo reaction. In the case of an exothermic reaction, this is an exothermic reaction, The reactants are at higher energy level as compared to the products. These are the reactants and these are the products. In other words, the products are more stable than the reactants. Overall, delta H for the reaction is negative, which means that energy is released in the form of heat. The activation energy is the minimum quantity of energy which the reacting species must possess in order to undergo a specified reaction. In case of endothermic reactions, the reactants are at a lower energy level compared to the products, as shown in the diagram. In other words, the products are less stable than the reactants, since we are forcing the reaction in the forward directions towards more unstable entities. Overall delta H for the reaction is positive, which means energy is absorbed from the reactants, and also the activation energy in this case is higher, and it is the minimum quantity of energy which the reacting species must possess in order to undergo a specified reaction. A number of factors other than concentration may affect the reaction velocity. Among these are temperature, solvents, catalysts, and light. According to classic collision theory, reaction rates are expected to be proportional to the number of collisions per unit time. Because the number of collisions increases as the temperature increases, the reaction rate is expected to increase with increasing temperature. In fact, speed of many reactions increases about 2 to 3 times with each 10 degrees rise in temperature. As a reaction proceeds from reactants to products, the system must pass through a state whose energy is greater than that of the initial reactants. This barrier is what prevents the reactants from immediately becoming products. The activation energy is a measure of this barrier. The effect of temperature on reaction rate is given by the equation first suggested by Arrhenius. This is the Arrhenius equation, where K is the reaction rate constant, A is a constant called frequency factor, EA is the energy of activation, R is the gas constant, and T is the temperature. The equation can be written as an exponential relationship, or as a natural logarithmic relationship, or just a logarithmic relationship. Accelerated stability studies. The stability of drug products need to be evaluated over time in the same container closure system in which drug product is marketed. In some cases, accelerated stability studies can be used to support tentative expiration dates in the event that full shelf life studies are not available. Accelerated stability studies are designed to increase the rate of chemical degradation or physical change of a drug substance or product by using exaggerated storage conditions. Data from these studies, in addition to long-term stability studies, can be used to assess long-term chemical effects at non-accelerated conditions. The method of accelerated testing is based on the principles of chemical kinetics. According to this technique, the reaction rate constant values for the decomposition of drug in solution at various elevated temperatures are obtained by plotting some function of concentration against time. The logarithms of the specific rates of decompositions are then plotted against the reciprocals of the absolute temperature, and the resulting line is extrapolated to room temperature. The reaction rate constant is used to obtain a measure of the stability of the drug under ordinary shelf conditions. These figures show how the accelerated stability studies are usually conducted. Drug solutions of known concentrations, as we mentioned, are stored at elevated temperatures such as 70 Celsius degrees, 60 Celsius degrees, 50
Celsius degrees and 40 Celsius degrees. The concentration of drug remaining undecomposed in solution is determined as a function of time. In this case, drug undergoing first order decomposition, a plot of log, this is log because this is a semi-log paper, a log concentration against time gives a straight line relationship. The value of the first order rate constant are obtained from the slopes of these lines. Okay. And then from the Arrhenius equation, log reaction rate constant versus 1 over T, the linear relationship is obtained. The resulting straight line can be extrapolated to 25 Celsius degrees, which is the room temperature, or to any other temperature. This extrapolated rate constant provides a measure of the stability under shelf life conditions. Drug chemical decomposition pathway could be hydrolysis, for example, could be oxidation, could be photolysis. This is an example on how the activation energy is being determined. The rate constant for decomposition of drug were measured at 5 different temperatures. The data are shown below. Plot Lin reaction rate constant versus 1 over T and determine the activation energy in kilocalories per mole for the reaction. These are the reaction rate constants at different temperatures are being used. These are the data for Lin reaction rate constant versus 1 over T. The Lin reaction rate constant is plotted against 1 over T, and the slope is used to obtain the activation energy. The slope equals minus activation energy divided by R. Therefore, the activation energy equals 14.575 kilocalories per mole. The students should learn how to use the linear regression on their calculators to determine the slope and the intercept in order to determine the activation energy. This is an example on how the Arrhenius equation is being used to determine the reaction rate constant at certain temperature. The rate constant of a first order reaction is 3.46 multiplied by 10 to the power minus 2 seconds to the power minus 1 at 298 Kelvin. What is the rate constant at 350 Kelvin if the activation energy for the reaction is 50.2 kilojoules per mole? If we know the reaction rate constant at 298 Kelvin, and if we know the activation energy for the system, and if we know the two temperatures, the one that at reaction rate constant 298 and the one that needs to be determined, the reaction rate constant at 350 kelvins can be determined. Example 14.3. The catalytic decomposition of hydrogen peroxide can be followed by measuring the volume of oxygen liberated in a gas burette. From such an experiment, it was found that the concentration of hydrogen peroxide remaining after 65 minutes, expressed as the volume in milliliters of the gas evolved, was 9.6 from an initial concentration of 57.9. A. Calculate the reaction rate constant assuming first order kinetics, and B. How much hydrogen peroxide remained undecomposed after 25 minutes. This is the equation for first order kinetics. The reaction rate constant can be determined from the initial concentration and the remaining concentration at 65 minutes. Then in part B, the remaining concentration at 25 minutes can be determined by knowing the initial concentration and the reaction rate constant from part A. Example 4. A solution of a drug contained 500 units per ml when prepared. It was analyzed after 40 days and was found to contain 300 units per ml. Assuming the decomposition is first order, at what time will the drug have decomposed to 1/2 of its original concentration? Okay. First of all, we need to determine the reaction rate constant from ln C equals ln C naught minus KT. The initial concentration is 500 units, and the remaining concentration after 40 days is 300 units. Therefore, the reaction rate constant equals 0.012 day to the power minus 1. The half-life of a first order reaction equals 0.693 divided by the reaction rate constant, and in this case it equals 54.3 days. Example 5. Walker investigated the saponification of ethyl acetate at 25 Celsius degrees. The initial concentrations of both ethyl acetate and sodium hydroxide in the mixture were 0.01 molar. The change in concentration X of alkali during 20 minutes was 0.00566 moles per liter. Therefore, A minus X equals 0.00434. Compute A, the rate constant, and B, the half-life of the reaction. This is the equation for second order reaction when the two reactants are present at the same concentration. If we have initial concentration is known as 0.01 and X equals 0.00566, then at 20 minutes, then reaction rate constant can be determined. Once the reaction rate constant is determined, we can determine the half-life of the second order reaction, which equals 1 divided by AK, and in this case the half-life equals 15.3 minutes.